Good morning, everybody. Okay, so today we're going to be looking at the last part of our notes on section 2 of chapter 14, fluid properties. Okay, now we've already, let me show you what we've already done. And where did I put it? Yeah, here it is. Hang on, guys. Okay, so we've already done Archimedes' principle, okay, about buoyancy and the buoyant force exerted by fluids. And we've also looked at Pascal's principle about the pressure exerted by fluids and what happens if you exert a pressure on a fluid. Okay, and we even learned about hydraulics and how to find the force in or the force out, and we've practiced some of that. Now, today we're going to look at a different property of fluids, okay? Now, this property was discovered by a Swiss scientist. Now, he was born in Switzerland, but his last name is actually Italian. His name was Daniel Bernoulli, B-E-R-N-O-U-L-L-I, Daniel Bernoulli. Now, he discovered an interesting property of fluids. Have you all ever been outside with a garden hose, especially like in hot summertime or something, and you squirt each other and you put your thumb over the end of the hose partially, and the water comes out faster if you do that? Well, there's a reason for that, and Daniel Bernoulli is the one who first understood what's going on when you squirt the water out the hose that way by putting your thumb over the end of the hose. Well, we call this idea that he discovered Bernoulli's principle. So this is the third principle we've looked at in this chapter. Archimedes' principle, Pascal's principle, and now Bernoulli's principle. Basically, he said when a fluid moves faster, its pressure that it exerts decreases. So the faster a fluid travels, the less pressure it exerts on its surrounding container. All right, so let's take a look. Here we have a water pipe, and the water is flowing from left to right, and there's three little vertical pipes that lead off. Now, I want you to notice there's three distinct sections here. The first section and the last section both have wide pipes, a large cross-sectional area here. So here, the water is moving fairly slowly. All of the water molecules that wrong direction, wouldn't you know it? All right, fix that so it goes the other way. Okay, there we go. Fix it so it goes that way. Okay. Now, when the water gets to this point where it narrows, all of those water molecules can't go through at the same time like they did here or like they do here. Because you see, each little cross-sectional area has a certain number of water molecules, but they can't all go through at once because they'd be crammed closer together, and water is not really very compressible, is it? So what they have to do is they have to take turns going through, and they have to go through faster in order for them to all get over here and fill up the area or fill up the volume again. So the fluid, as it goes through, it increases speed, it increases velocity and goes faster. Then it decreases speed as it fills up the larger areas on the other side. Now, what does that have to do with pressure? Well, look at the three little vertical pipes. In the areas where the pipe is wider and therefore you have a lower velocity, it creates more pressure, so more water is pushed up the vertical pipe. But in the area where the water goes faster, less pressure is created by that, the water does not go up the pipe as high because there's not as much pressure underneath it to push it up. So, high pressure, low velocity. Okay? And low pressure, high velocity. So, the faster a fluid moves, the less pressure it creates. Now, I'm going to be showing you guys some videos in the next couple of days, and one of them is going to have some very interesting little demos in it that are going to show you some interesting things that can be shown with faster and slower moving fluids. One of them has to do with two balloons that are hanging near each other with a space between them. And what you're going to see is they're either going to take a straw and blow air between the two balloons, or they're going to take a water hose and squirt water between the two balloons. In either way, the fluid, whether it's air or water, the fluid that is passing through the two balloons is going to decrease, because if you have a high velocity, you have a low pressure. But the air pressure on the other sides of each balloon hasn't changed because the air is just moving normally. It's not moving as fast as the fluid in between. So here you have a high pressure because you have a low velocity compared to the center. And the same thing on this side. High pressure because you have a low velocity. And that is going to cause the balloons to be pushed towards each other, pushed towards the low pressure, because objects want to move in a direction from high pressure to low pressure. A higher pressure exerts more force, so it moves things towards a lower pressure where there's less force pushing back. So the balloons get pushed towards each other. Isn't that kind of neat? And we're going to see a video where that takes place. Now, this is also the reason that those gigantic airplanes can stay up in the sky. Let's talk about that for a minute. As you guys know, these big jumbo jets, in fact, any airplane, has engines that provide a forward thrust on the plane. This forward thrust makes the plane go forward, yes, but it doesn't keep the plane from falling out of the sky. Gravity pulls down on the plane. So we need something to balance the gravity in order to keep the plane from falling out of the sky. Well, this is where the shape of the wing comes in. An airplane wing is shaped so that it's flatter on the bottom and more rounded over the top. So if you had two air molecules and they reach the front of the wing, one is going to go over the top of the wing, one is going to go underneath. The one going underneath travels much less distance because it's flat and reaches the back. The one that goes over the top of the wing has to travel much further distance. And it would, you would think, get back to it would take it longer to reach the back than the other one on the bottom. But here's the problem. If the one on the top takes longer to get to the back, then there's nothing back there to fill the void. So you've produced a vacuum over the top back end of the wing. Now, nature abhors a vacuum. It wants to fill it as quickly as possible. So in order to fill the void left by the air that's not gotten back there yet, what happens? Well, the air that goes over the top has to fill that void. How can it do it? It travels faster than the air going underneath, so that it does get to the back in time, okay? So the air underneath goes slower, and the air on top goes faster over the wing to fill the void, and it all gets back there at the same time. Now, what does that have to do with Bernoulli? Well, the slower air underneath, because it is moving slower, creates a lot of pressure and therefore a lot of force underneath the wing pushing up. But the faster air on top produces less pressure, so it pushes down nowhere near as hard as the pressure underneath. So, oops, there's the clock. Okay, so if you have more force underneath pushing up and less pushing down, the difference pushes up, and we call that difference lift. That's the aeronautical term for it. It's called lift. And lift is what balances the gravity, the weight of the plane and its load of luggage and all the people. That lift is what keeps the plane from falling out of the sky. Okay? So the faster it moves over the top compared to the bottom, the more upward force or lift you create. So the faster the plane goes, the more lift is produced, and it stays up in the sky rather than falling to the ground. Now that's pretty cool. All right, here's another example of what fluid pressure and velocity can do for us. Have you ever seen someone, like in this picture, outside in their yard with an attachment on their hose to spray, say, fertilizer or maybe pesticide on their bushes or their grass? And this attachment, they're not squirting with it, okay? There's no squirting. He's actually just holding it as the water comes through and he's spraying it. But how does the insecticide / fertilizer get from the container into the water that's spewing out the nozzle? Well, it's Bernoulli, okay? The hose, and here's the hose, is wider, but the straw that goes through to the nozzle is narrower. So the water speeds up when it goes through this little tube. And when it speeds up, it creates a low pressure area. The contents in the bottle are under a much higher pressure. So the difference in pressure forces this insecticide / pest or insecticide / fertilizer up through the straw to the low pressure water. And it mixes with the water and comes out through the nozzle with the water. Okay? So the straw transmits the fluid from high pressure to the low pressure created by the water in the tube to mix it with the water so it gets sprayed on your shrubbery or your grass for whatever you need. Kind of neat, huh? Okay. So that's Bernoulli. The faster a fluid moves, whether it's a gas or a liquid, the faster it moves, the less pressure it exerts. Okay, now let's look at one last property of fluid. There's not a lot to it, so we're going to go ahead and talk about it instead of spending another whole page or something on it. And that is the property of viscosity. Now, viscosity is the resistance of a fluid to flowing. And typically, the denser a fluid is, the more viscous it is. Now, what do we mean by that? Well, let's just think of some examples of viscous fluids. Honey is an example. It is a fluid. It flows, but it doesn't flow like water. Water is really runny, but honey is not. It sort of oozes, doesn't it? But it's still a fluid. We call it viscous because it does have a resistance to flowing. Other examples would be syrups or chocolate sauce, oils, different kinds of oils, not just the kind you eat, but mechanic oils and stuff. Mustard and ketchup. Those are just some examples of fluids that are viscous, okay? Now, you can actually change the viscosity of a fluid by using temperature. For example, if you've ever tried to change the oil in a car on a cold day, you will find that the oil drips out at a much slower rate on a cold day than it does on a hot day. In other words, when they're colder, they become more viscous. That's true for any viscous fluid. Honey, if you put honey in the refrigerator, it's going to take it more time to ooze out of the bottle than it would on a hot day. When they're warmed up, they become less viscous or more runny. Okay? So for a viscous fluid, the colder it is, the less runny it is. The hotter it is, the more runny it is. Okay? All right, now, another thing. Because they're denser, they can also provide more buoyant force than runnier fluids like water. Okay? So that means, if you remember the lab we did with Archimedes' principle, where we used the different metal cubes and the cube of wood and plastic, and we also used a rubber stopper. And we know that the rubber stopper, what did it do in the water? It sank, right? The rubber stopper sank in water, which has very little viscosity. It's very runny, isn't it? Okay, water only starts to get viscous when it's going into a freezing state, doesn't it? All right, but the stopper sank in the water. All right, it wouldn't sink in honey, a very viscous fluid, because the honey is denser. It has more mass per unit volume, which means when the stopper displaces a volume of the honey, the weight of the displaced honey is more than enough to counterbalance the weight of the stopper and support it. So the rubber stopper will float in honey, whereas it would sink in water. Okay, that's kind of neat too. All right, so that's the end of this set of notes. And we've looked at Archimedes' principle, we've looked at Pascal's principle, and now Bernoulli's principle, and also viscosity. And tomorrow you're going to look at some videos on Bernoulli's principle and answer some questions so that we know we understand. And if I can find one, I'll see if I can find a little sort of lab activity that you can do online with Bernoulli's principle. I think there is one or two out there, and I'll look for them, okay? All right, you have a good day. Talk to you soon. Bye-bye.